Hi, this is Mrs. La Barbara. Today's topic is motion diagrams. The objectives for today is know how to interpret motion using ticker tape diagrams and how to interpret motion using vector diagrams. Be able to construct a ticker tape diagram and a vector diagram with given word description of motion. Ticker tape diagrams. A common way of analyzing the motion of objects in physics lab is to perform ticker tape analysis. So a long tape is attached to a moving object, such as the cart, and thread through a device. This is a device called spark timer. And this device will leave a tick on the tape at regular intervals. Usually the time between the interval is 0.1 second. As the object moves, it would drag the tape through the ticker and leave a trail of dots. So the trail of dots provides a history of object's motion and therefore a representation of the object's motion. So these are examples of the ticker tape left behind, the trail of ticker tape. So we can use these dots to analyze how the object has moved. As you can see, let's compare these three. The top one looks like it's moving at a constant speed. How do we know? Because each time interval is the same and the distance between them also the same. The second one looks like the distance is increasing slightly. So look at the last is a lot further than in the beginning. That means it's accelerating. The last one also indicates acceleration. So how can we compare the acceleration between the last two? Well, the last one, acceleration is bigger. As you can see, the distance increasing at a greater rate. So here are examples of ticker tape. What can we say about this ticker tape again? First is constant motion. The second one is also constant. So what's the difference between these two? The first one is faster because the distance between the time interval is more than the distance between the time interval of the second ticker tape. Fast and slow, they are both constant. Let's take a look at this group. The first one is constant. This one, the one in the middle, says it's accelerating, so because the space is increasing. The last one is also accelerating. How do we compare the acceleration between the last one and one before that? This acceleration is bigger because it increased at a greater rate. Lots of acceleration. Here is an example. Oil drips at 0.4 second intervals from a car that has an oil leak. Which pattern best represents the spacing of oil drops as the car accelerates uniformly from rest? So it's constant acceleration. So which one represents constant acceleration? Well, not the first one. The first one says there is no acceleration. It's constant velocity. The second one says, oh, there is acceleration. Let's see the third one. Looks like there is acceleration also. But if you look at it closely, the first three says it's constant. Then from the fourth to fifth, okay, this three says it's accelerating. That last one is constant again. So it's constant, accelerate, constant. So acceleration is not uniform. Acceleration is not constant. The last one is just velocity is changing. Acceleration is not constant. So the answer to this question is B. Another example. A spark timer is used to record the position of a lab cart accelerating uniformly from rest. Each 0.1 second, the timer marks a dot on a recording tape to indicate the position of the cart at that instant as shown. The linear measurement between t equals 0 second to t equals 0.30 second is 5.4 centimeters. Calculate average speed of the cart during the time interval t equals 0 second to t equals 2.30 seconds. So what is the average speed? So average speed equals total distance divided by total time. Total distance in this case is 5.4 centimeters and total time is 0.3 seconds. So the average speed is 18 centimeters per second. You don't have to convert this to meters per second because it didn't ask you to convert. Another example, consider the word description of motions of object A, B, and C and construct corresponding diagram on the ticker tapes. So A says moving with constant velocity. If velocity is constant, the dots has to be even, so it should look like this. The second one says slowing down. If it's slowing down, that means dots has to become closer and closer to each other. Looks like that. Third one says speeding up. That means dots has to be spread further apart. Looks like that. Vector diagrams. Vector diagrams are diagrams that depict direction and the relative size of the vector quantity by a vector arrow. So here is an example of a vector arrow. So here is vector, looks like they have the same size and same direction. So what can we conclude from this diagram? V is constant, so constant velocity. Looks like this. This is also a car driving, but the size is getting bigger and bigger. So that means velocity is increasing. It's accelerating. Here is another example of vector diagram. Looks like this one indicate acceleration vector. So looks like acceleration vector has the same size for all of them, and the direction is also the same. So what can we say about acceleration? It is constant. Take a look at another example. So this one shows the direction in the velocity in the x direction and velocity in the y direction. What can you say about Vx? Well, Vx have the same size, so Vx is constant. What can we say about Vy? Well, the size of Vy over here has nothing. Over here is increasing, so Vy is increasing. So speed is increasing in the vertical direction. In the horizontal direction, velocity is constant. That's it for today. See you next time.